Welcome to my video lecture. This is Amarnath, Assistant Professor in Mathematics. Today I am going to handle linear algebra and calculus, one of the topic, diagonalization of a matrix. We are taking the third part of this diagonalization. In earlier class, we have discussed about the algebraic and geometric multiplicity of an eigenvalue. This we have discussed, algebraic and geometric multiplicity. In present lecture, we discuss about the diagonalization of real symmetric matrices. What is the difference? The previously is not particular, it is general. For any matrix we have done, but for real symmetric matrix we have some flexibility and some different properties we have. That is called as a orthogonal reduction that we are going to do. That is diagonalization of real symmetric matrices. So what is mean a real symmetric matrix? Right. So real symmetric matrix in the sense, a matrix A is said to be real symmetric if it is real and symmetric property. A transpose is equal to A. That is called real symmetric matrix. So two real symmetric matrix. Right. Let us see the small example, then you will understand. Suppose A is equal to, we have a matrix, right? That is 1, 2, 3. Let us take 1, 2, 3, 0, minus 1, minus 1, 4. Look at this matrix. It is a real matrix as well as symmetric. How can we say it is a symmetric? So if you transpose, even you transpose, A transpose is equal to A we get. That is, first row is equal to first column, second row is equal to second column, third row is equal to third column. You can check it. Clearly, even we transpose, we get the same matrix. That is called real symmetric matrix. For this type of real symmetric matrix, how to do the diagonalization? Earlier we do the diagonalization process. To continuation to the diagonalization process, we will discuss about the diagonalization. This is orthogonalization we can say. So let us discuss with the procedure how to do the diagonalization. Now, so clearly here I am going to explain how to do the diagonalization. This is called also orthogonal diagonalization or orthogonal reduction also we can call. So in this procedure, first for the given matrix A, let us say one symmetric matrix is given. A is symmetric, so suppose real and symmetric, real and symmetric, real and symmetric is given. Then first we need, like as the earlier process, first we find eigenvalues as well as eigenvectors. That is, we know how to find eigenvalues, eigenvectors very well. We have discussed in the previous lectures very well. Now, then after finding the eigenvectors, to each eigenvalue, suppose we got 3 eigenvalues, 3 by 3 matrix, then we find 3 eigenvectors. So like we are calling as x1, x2, x3. Let us say we got lambda 1, lambda 2, lambda 3 are the 3 eigenvalues. Then corresponding eigenvectors are x1, x2, x3. So here, since it is an orthogonal reduction, we have to verify orthogonality of the vectors. Orthogonality vectors in the sense, the 3 vectors which we obtained, eigenvectors, that must be orthogonal to each other. Then how to check orthogonality each other? They are perpendicular to each other, x1 and x2 and x2 and x3 and x1 and x3, whatever the possible 3 mutually. You take any 2 out of the 3 eigenvectors, you take any 2 eigenvectors that should be perpendicular to each other. Perpendicular in the sense their dot product is 0. We know in the vector concept, 2 vectors are said to be perpendicular to each other, that is cos 90 is 0. Then A dot B is equal to 0, then A comma B we can call it as the orthogonal vectors. So here we need to verify orthogonality of the 2 vectors. That is how to check. Suppose x1 and x2, we have 2 vectors. Then 2 vectors are said to be orthogonal to each other. x1 dot x2 transpose is equal to 0. Why I am writing transpose? Means both are column vectors, we can't multiply. Let us say example, x1 is equal to, I have 1, 0, 2. Next, x2 is equal to, I have, let us say 0, 2, 0. Then directly I can't multiply these two. The multiplication is not possible. That's why one matrix should be transposed. x1 dot x2 transpose. So directly we can say here first element, multiply 1 into 0, 0 plus here second element, here second element multiply 0 into 2, 0, add all the summation 2 into 0, 0. So, this is clearly 0. Then I can say x1 comma x2, x1 and x2 are orthogonal to each other, orthogonal to each other. Like that, we have to verify all possibilities x1, x2. Similarly, x2 dot x3 transpose is equal to 0 and x1 dot x3 transpose. All three possibilities x1, x2, x3 we have to check individually x1, x2, x2, x3, x1, x3. All dot products we find. Suppose all the dot products are 0, then we can say the three vectors are mutually orthogonal to each other. If not orthogonal, what to do? We need to change any one of the value of the eigenvector so that they become perpendicular to each other. That we discuss in the problem. So, generally first condition for orthogonal, this is the verification is very important, right. Let us then next, after getting the eigenvectors, we need to form model matrix with normalized eigenvectors. Next step, model matrix. What model matrix should contain? Normalized eigenvectors. So, then what do you mean by normalized eigenvectors? So, here model matrix generally we write P. P means here we call x1 cap, x2 cap, x3 cap. Cap is normalized eigenvectors of x1, x2, x3. Then how to do that normalized eigenvectors? Let us say example you will understand. Suppose x1 is equal to we have 1, 1, suppose 2. So, what is the normalized eigenvector? Means this is x1 by norm of x1 is called x1 cap. What do you mean by norm? Norm means length of the vector. We know very well how to find the length of the vector. That is under root. So, 1 square plus 1 square plus 2 square. How much that value? Root of 1 plus 1, 2, 2 plus 4, 6. Root 6 is the norm of the vector. Then automatically, what is the x1 cap? Here I will get x1 cap is equal to, so we should divide the x1 vector, divide with it x1 norm. That is how much? Root 6. What is x1? Given vector. What is a given vector? 1 comma 1 comma 2 is a given vector. That is you are dividing root 6. Nothing but that is 1 by root 6, 1 by root 6, 2 by root 6. This is a normalized eigenvector. Okay. So, one vector, once we get the one vector, you find the norm and divide the each value of the vector with its norm. That is called normalized eigenvector. So, I have done for x1. Similarly, we got another two x2, x3, that also we find. So, then divide with its norm x2 cap. x2 cap means normalized eigenvector of x2. Divide x2 with x2 norm. Next here x3 cap. Similarly, x3 by norm of x3. Okay. So, like this we find three normalized eigenvectors, all three together we call model matrix. So, earlier in the diagonalization, what is the difference? Earlier just we took x1, x2, x3, the only eigenvectors we took, but it is an orthogonality case. So, since here three matrices, three x1, x2, x3 are mutually orthogonal, then P will become orthogonal matrix. Why? Because these any two rows you are taking orthogonal, then P is a orthogonal matrix. Orthogonal matrix. For orthogonal matrix, we have a property, right? Let us discuss the orthogonal property. Now, since P is orthogonal, we are deciding P is orthogonal. P is orthogonal means we have a property P inverse is equal to P transpose. P inverse is equal to P transpose. How it is possible? Then we have the property P into P transpose is equal to I. Why, sir? So, this is a orthogonal property. Since it is an orthogonal matrix, we have the property A into transpose is equal to I. So, now here if I transpose the P to other side, that will become P inverse into I. Then P transpose will become P inverse. So, here just you transpose the matrix, you will get inverse. So, clearly P inverse of the matrix, whatever we have done the model matrix, just to transpose the rows and columns, you will get the inverse. But actually finding inverse for other matrices, it is very difficult. We need to find 1 by det A. Suppose you want to find A inverse, then how will you do generally? 1 by det A into adjoint of A big process. That is for general matrices. But in particular orthogonal, we have a facility, that is P transpose is equal to P transpose. Since our process P becomes orthogonal, we have this facility P inverse is equal to P transpose, right? Then the last step in the procedure, diagonalization. Already we know the formula diagonalization, P inverse AP is equal to D. Okay, P inverse AP is equal to D. Already we have the P matrix, model matrix. If you transpose, you are getting P inverse. A is a given matrix. Multiplying these three matrices, you have to get the diagonal matrix, where what is the diagonal matrix? D is equal to, which contains diagonal elements as the eigenvalues, lambda 1 0 0 0, lambda 2 0 0 0, lambda 3. This is a diagonal matrix. Okay, this we call it as a diagonalization. So since we are getting the exactly diagonal elements and remaining elements are 0, our process has been done, and we are calling this a diagonalization. By which type of we are doing? By orthogonalization. How you are saying this orthogonalization process? Because the matrix we used here, the matrix we used is orthogonal. That's why we can call this process is orthogonal diagonalization or orthogonal reduction. Whereas other diagonalization, other matrices, we don't use the orthogonal matrix, right? Let us explain with this example, right? Diagonalize the matrix. Here I have taken one matrix by orthogonal reduction. So the procedure we learn, as per the procedure we follow, right? So let us prove the, let us find the orthogonal diagonalization. So given matrix, we need to find eigenvalues. Find eigenvalues. How to find eigenvalues? We know very well. Det of A minus lambda I is equal to 0. A minus lambda is equal to 0 means det of 1 minus lambda 0 0 0 3 minus 1 0 minus 1 3, right, is equal to 0. 3 minus lambda is equal to 0. So from the diagonal elements you subtract the lambda. So then how to find this one? This is directly, we have a formula we have discussed in the previous classes. Finding eigenvalues, lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. It is a chaotic equation, shortcut formula. Otherwise you expand any one of the row, you can get it, anything is okay, right? We have discussed the two methods of finding eigenvalues. Now s1 is equal to trace of A. How much that is? 1 plus 3 plus 3. So 6 plus 1, 7. S2 is the det of diagonal elements, that is the cofactors 1, 3, 3. So cofactor matrices sum we need to find. So leaving the first one and the det of remaining 3 minus 1 minus 1 3 plus, now second element 3, leaving this row and column 1 0 0 3 plus leaving this third element. So 3 elements, first element leaving the 1 row and column 3 minus 1 minus 1 3, second one leaving the second diagonal element, that is the corner element 1 0 0 3. Next leaving the third diagonal element, leaving this row and column 1 0 0 3, right? This we can find how much that is, how much we are getting, finding this S2 value, that is 14. That is, you know, simplification process you can do. Then S3, what is the S3? Det A, det of this matrix we know very well how to find, that is 8. Now substituting in the equation, we are getting the lambda cube, substituting S1 S2 S3, lambda cube minus 7 lambda square plus 14 lambda minus 8 is equal to 0. It is a chaotic equation. It is a third degree chaotic equation. Solving 3, we get 3 eigenvalues that are called roots of the equation. Let us say lambda is equal to the 3 eigenvalues 1, 2, 4. So this you need to solve. Solve means we can use scientific calculator, find the roots by factorization, or synthetic division method, anything you can use. So, these are the required eigenvalues. We have done so many problems in the previous lectures finding eigenvalues. Next, first step completed. Next, we need to find eigenvectors. So, then eigenvectors. So, what are the eigenvectors? How to find eigenvectors of the matrix? That is A minus lambda I into x is equal to 0. This is the formula to find eigenvectors. That also we discussed very well. Now, put lambda is equal to 1 and 2 and 4. Solve. We get the 3 eigenvectors. So, here I am writing directly the eigenvectors, that is first eigenvector for lambda is equal to 1, right, 1 0 0. Next, x2, second eigenvector 0 1 1. Next, third eigenvector x3 is equal to 0 minus 1 and 1. These are the 3 eigenvectors we get solving the A minus lambda I into x is equal to 0. We discussed very clearly in the previous lectures, right. Now, let us check the orthogonality. So, after finding the eigenvalues and eigenvectors, since our reduction is orthogonal reduction, find orthogonality or verify the orthogonality. How to verify the orthogonality? So, just now I said their dot product is 0. Let us discuss x1 dot x2 transpose. x1 means 1 0 0 and x2 transpose 0 1 1 transpose, right. So, this one we can find it, right. Now, so then dot product, how to do? I said multiply the corresponding element, first 1 into 0 0 plus 0 into 1 0 plus 0 into 1 0, the summation is 0. Then we are calling this is a two vectors are orthogonal to each other. Similarly, we find other two vectors x2 dot x3 transpose. x2 is the second vector 0 1 1 and x3 transpose 0 minus 1 1 transpose, means we can multiply the matrices. Now, 0 into 0 0, here second element 1 into minus 1 minus 1, here third element, here third element 1 into 1 1, sum of these 3, that is 0. So, and x2 and x3 are orthogonal to each other. Here x1 x2 orthogonal to each other, and one more possibility, first and third, that is x1 dot x3 transpose. Let us find, that is x1 1 0 0, right. x2, what is x2? Sorry, x3 is 0 minus 1 1. Again there dot product. So, first elements multiply 1 into 0 0, 0 into minus 1 plus 1 into 0 into minus 1 0, and here that is, this is also 0. 1 into 0 0, 0 into minus 1 0, 0 into 1 0, total is 0, and x1 x3 also orthogonal. Hence, what we can conclude, x1 x2 x3 are mutually orthogonal. This is a very very important, mutually orthogonal. So, this is because our reduction is orthogonal reduction. The matrix which you are using, model matrix, must be orthogonal. Then normalized eigenvectors we have to form. Then we need x1, x2, x3. Then x1 cap, let us find. x1 cap means norm x1 VV. Just now we discussed how to find the normalized eigenvectors. x1 length, how much x1 length? So, 1 square, 0 square, length of the first vector, that is 1. Then x2 norm, that is x2 norm is length of the second vector 0 square, 1 square, 1 square. How much? That is root 2. Next, third eigenvector x3 under root of how much? That is the third eigenvector 0 square minus 1 square, 1 square, 0 square minus 1 square plus 1 square, which is equal to root 2. So, these are the norm. Then each vector value must be divided with its norm. Then we have discussed the formula, x1 cap is equal to x1 by norm x1, x2 cap is equal to x2 by norm x2, right. x3 cap is equal to x3 by norm x3. Right. What is the modal matrix we should form here? Modal matrix P is equal to x1 cap, x2 cap, x3 cap. This is our required modal matrix with the normalized eigenvectors. Then how to write the modal matrix here? I am writing that is the first eigenvector 1 divided by 1 only, second eigenvector divided by with root 2, third eigenvector divided with root 2. That will give the required modal matrix. Let us write the modal matrix. P is equal to, again I am writing here, x1 cap, x2 cap, x3 cap, that is equal to first eigenvector 1 divided by 1 only. So, 1 0 0, 1 divided by 1, 0 divided by 1, 0. Second eigenvector divided by root 2, 0 by root 2, 1 by root 2 and 1 by root 2. Second eigenvector. Each value divided with norm. What is the norm of the second eigenvector? Root 2. Third eigenvector also root 2. Third eigenvector first value 0, 0 by root 2, 0. Second value minus 1, minus 1 by root 2. And third value 1 divided by root 2, 1 by root 2. Okay. This is a P matrix. So, clearly it is orthogonal, no doubt. How can we say it is orthogonal? Since we have any two columns orthogonal to each other, definitely P is orthogonal. Since P is orthogonal, we know P inverse is equal to P transpose. So, inverse you no need to find, directly transposing the rows and columns we get the inverse. That is the specialty of orthogonal matrix. So, I said how it is orthogonal, we have this facility also, just I multiplied and shown with the definition. Now, P inverse, let us write P inverse by making transpose. First row as a first column 1 0 0, second row as second column 0 1 by root 2 and minus 1 by root 2. Second row, third row means 0, this one 1 by root 2, 1 by root 2, right. We got the required P inverse. Now, diagonalization. For the diagonalization formula, I gave you the procedure, that is P inverse AP is equal to D. We have P matrix, P inverse A, multiplying these three. So, let us write P inverse. We have 1 0 0 0 1 by root 2, 1 by root 2, 0 minus 1 by root 2, 1 by root 2. This is P inverse into A. A means given matrix. What is the given matrix here? For this problem we have taken 1 0 0 0 3 minus 1 and 0 minus 1 3. This is a given problem which one we are diagonalizing into P. So, P matrix is, which is a modal matrix, 1 0 0, next 0 1 by root 2 minus 1 by root 2, 0 1 by root 2, 1 by root 2, right. This is P inverse first matrix, this is a given matrix A and P is a modal matrix. Multiplying these three matrices, we get a diagonal matrix. How to multiply? Very simple. In the scientific calculator we can use, or we can do manually. So, enter in mat A, enter in mat B, enter in mat C in scientific calculator. So, mat A into mat B into mat C, you can directly you can get the product. Instead of doing manually, since the students are allowed to use the scientific calculator, multiply with the using scientific calculator. That's the result will be directly we are getting the diagonal elements, that is 1 0 0 0 2 0 0 0 4, right. So, clearly it is a diagonal matrix. See, the diagonal elements are non-zero, remaining elements are 0. What do you call this one? D. So, clearly we got P inverse AP is equal to D. So, this is orthogonal reduction, orthogonal transformation. Similarly, the same type of orthogonal reduction we repeat in the quadratic forms also, this type of reduction, because the quadratic forms will be converted to symmetric matrix, then same type of process will be coming. There again we discuss about this orthogonal reduction. Now, a symmetric matrix is given, how to do the diagonalization we have done. So, look at this one. So, in this session clearly we discussed diagonalization of real symmetric. In particular case we are doing, it is a symmetric matrix, that is A transpose is equal to A. Such type of matrix is given, then that we have discussed very clearly. Now, in the next class we discuss about the Cayley-Hamilton theorem and its applications that we have done, and quadratic forms also we will be doing. Next class we discuss about quadratic forms, right. So, Cayley-Hamilton theorem already we have done, then we can do the quadratic forms which is related to the orthogonal reduction also, right. Thank you.